there's a resolution limit for this, right? And the resolution limits depends on the wavelength and the numerical aperture. This has to do with your optic system, right? So since the wavelength of light is in the nanometer range, right? That you can see here from 4 to 700 nanometer in the visible light. We are limited by the wavelength, right? And we get a resolution limit. If we had amazing, the best optics in the world, we could have like a few, hundreds of nanometer resolution limit. But instead of this, we use electrons. The wavelength is much smaller and resolution limit is much smaller. So we can measure much smaller features in the nanoscale. And to give you an idea, depending also on the energy of the electron, the wavelength can be from 10 kb. For example, the wavelength can go to picometer. So the resolution it's enhanced a lot if we go to electrons, right? So for this, we're using an SEM. This is, if you guys sometimes come here to our lab, you'll see the instrument that we have is this guy over here. And since you cannot see it from the camera, I'm gonna walk you a bit through the process and through the components, so you guys know more or less how this thing works, right? So this is basically, for some reason, I'm sorry, the mouse is giving me some problems, I'm sorry. This is pretty much a diagram with the 2 or 3 components of the microscope. So this one over here, this is the sample chamber, right? And this is the electron gun, the column chamber, right? So in here we have the electron generation at the top, at the electron gun, and they're accelerated through several anodes. They go through some magnetic lenses, and they hit our sample, right? Oops. But for this, we need vacuum, right? We need these conditions. Does anyone more or less know why, or can imagine why we need vacuum? Any ideas? Okay, so if we have electrons here at the top, right? The electrons have to travel all the way down to the sample, and then go to the detectors, right? So we need to have a very large mean free path. That means that is the distance, right? The mean free path is the average distance a particle can travel through free space without hitting another free particle. So we have some air or some other molecules in there. It will travel a much shorter distance before hitting some other stuff, and then the electrons will never reach our sample, and then we'll definitely not go back to our detectors. And this is why we need a high vacuum in the sample chamber to 10 to the -7 torr, and also vacuum in the electron gun column for also give mean free path and for preventing the tip from going back. So right now we have 10 to the -10 torr, which is like it's pretty high vacuum. Okay, so that's one thing that we need to operate the system. And then, as I mentioned, the electrons can travel from the top to the bottom. And we have several detectors that we're going to use the in-lens detectors for secondary electrons, but we will do some other SEM modes. We will not go over those today, but they're available in this instrument. And we have a bunch of lenses, and coils that will help direct our electron beam, and I'll go over that in a minute. Okay, so why SEM and why FESEM? FESEM stands for field division, right? So typically you can have two sources of electrons, right? The thermionic, which pretty much you're flowing a large current through a wire until it goes incandescent, and it emits electrons, right? Like you, similarly to a light bulb, right? But in a field effect electrons, we're using a tip that, due to the small geometry and these big, large electric potentials, electric fields that we have, the electrons are pulled through that with much, giving much better resolution and a much smaller electron beam. Just to give you comparative parameters, so this is the spot size, this is a regular SEM and a FESEM like the one we have here. As you can see, this has one more zero. But the spot size and the magnifications that these instruments are capable are much better, and we have a better resolution with this instrument. And this is an example of the tip for an FESEM. And maybe we can take a look at the one that we have in the instrument loaded. But as you can see, this is very, very small. So we can go. Here you have the scale bar, so you can see more or less that the tip is very sharp, right? It's like 400 nanometer. And this geometry is that it's emitting this large electron flux. Does it make sense so far? Okay, so what do we do to operate the SEM? So basically, there are a bunch of coils, magnetic field, magnetic lenses that, depending on the intensity of the current that goes through here, we can modify the magnetic field, and the magnetic field will deflect the electron beam. So changing this, controlling this, we can focus, and defocus, we can control the beam so it hits right at the surface. The problem with these lenses that it does not happen with optical microscopy is that they generate the higher magnifications. They have they generate aberrations, right? And they have some artifacts. And we have different. I think it should be here. We have different aberrations and different lenses to correct the thing. So in today's remote access, you will be able to move around the samples, because this stage can move in X, Y, and Z direction. And I will be controlling the focusing and correcting any problems with aberrations that we have so far. Good? Does that make sense?